As a part of the Modern Product Design class for the University of West Florida's Mechanical Engineering Department, a group of 5 engineering students teamed up for one common goal. We were tasked with creating a children's toy for the University of West Florida's Educational Research Center for Child Development. After a visit to the ERCCD, where we interviewed teachers and watched the children play with different toys, we were given 5 major customer needs to work with. The toy had to be educational, creative, unique, usable, and adaptable. With these criteria in mind, there was one toy that already met our customer needs, but we wanted to improve upon it. We based our toy off of the Unifix cubes, but wanted to make them more creative, educational, and usable. Starting with our customer needs and a base product, we got to work on our design. We used a black box model and a functional model to understand the flow of our design and the types of energies that our toy will use. From here, we started to design the actual product. We used the evaporating cloud method, a morphological matrix, and 3 different biological designs to generate 13 different variances that we would later slim down to one final design. Our design differences were shapes, connections, and the size of our product. Since we were looking for one design, we had to find a way to turn our 13 designs into one. We used both a weighted and an unweighted pug chart. This brought us to our final design. We chose medium-sized pieces with about 1-inch cross sections. They have differing shapes, and the connections are magnets inside of different shaped intrusions and extrusions. Throughout the project, we had 3 different prototypes. Let's start with our first prototype being our proof of concept. It was made out of 1.5-inch wooden cubes with 20 by 5 millimeter magnets. It let us get a feel for the approximate size and shape of our product and let us know what size magnets we would actually be using. From this, we learned there was no need for such large magnets, and so we reduced the size moving forward. When it came to our alpha prototype, we had pieces that looked much closer to a finished product. We printed 1 sphere, 1 cube, and 1 triangular prism-shaped piece, which each only had 2 extrusions. It was printed out of an ABS material and had 1 by 5 millimeter magnets. We printed a total of 3 pieces since it was not our final product and we just wanted to know how well they worked. Before making our final beta prototype, we did a design of experiments to test the strength of the magnets. We wanted to see if the male or female extrusions produced a stronger magnetic force and if the different shapes made a difference in the attraction. We found that none of these factors really made much of a difference, but it did help us solidify that the 1 by 5 millimeter magnets were the right size. After 2 different prototypes in the DOE, we were ready to make our final beta prototype. We printed this out of PLA material since we printed 30 pieces and it was much cheaper than the ABS used before. The other major difference between our alpha and our beta prototype is that we added more extrusions and intrusions to each piece. To construct the pieces, we first start by 3D printing. It takes about 24 hours to print all 30 pieces. We then move into spray painting the pieces. It takes about 30 minutes to dry before we can then do the final step, which is gluing in the magnets. This took us about 1 hour to complete. To use Snappables, you match like-shaped extrusions and use them to build creations. They can be used for counting and basic geometry lessons as well. We wanted to test on the children at the ERCCD, but due to a no filming policy, we had to use some of our fellow college students to play with them and give us their honest feedback. The feedback we received was that they loved the idea. It was very fun and creative. The only downfall was that some of the pieces had trouble fitting together, which is due to the caliber of the 3D printers on campus. Moving forward, if we were to mass produce the product, we would look into injection molding. This would increase accuracy of clearances and decrease prices.